Tom?
Good. All right, am I on? I am. Great, thanks. I'm Tom Libby. I'm a postdoc at the University of Washington with Sam Burton and Tom Daniel. But today I'm going to be talking about some of the work I did at the end of my PhD with Bob Full at UC Berkeley. So study running in a variety of animals, from cockroaches to horses, is characterized by high stereotypy in body forces. Sorry, this is not very bright. In kinematics and in gait. And this stereotypy may arise from things like energetic cost landscapes, stability basins, neural oscillators, et cetera, and has led to the discovery of many fundamental principles of how animals accomplish steady locomotion. But a lot of the behaviors that are really most interesting and potentially important are fundamentally unsteady behaviors, and we'd like to glean principles for those kind of behaviors as well, right? So can we get force patterns and gait patterns for something like this behavior? There's relatively little in the literature so far, but one principle that we can pull out is that animals can induce turns by small perturbations from their steady gaits. So this is a cockroach here accomplishing a turn by essentially extra added noise on top of their steady gait, and that leads to behaviors that are fundamentally not stereotyped because there are lots of little solutions they can use for the same gait. On the other hand, I'd sort of imagine that as you push an animal to turn harder and harder and harder, it's going to start impacting sort of fundamental mechanical constraints on things like muscle power or friction or posture, the forces you can generate in a particular posture. And you could hypothesize that this might push an animal to a single solution to a task, so more stereotypy. Or alternatively, I could imagine the same constraints could essentially induce more variation as animals are unable to respond to perturbations because they have really nothing left in the tank. So to probe this question, I set about trying to elicit a high-effort maneuverability task in a quadruped. That task looks like this in real time. It's fast, and that's because it's a prey capture behavior. So this is a red-headed agama. It's about a 100-gram lizard that I've used for a long time. And it's trained up to chase a cricket and capture a cricket that's been thrown about 2 body lengths behind it. This is a live cricket, so it induces a pretty well-defined task structure where the animal, in a short amount of time, has to turn around and run and grab the cricket before it hops away. Here's what that looks like slowed down. So there goes the cricket. And after a short time, the lizard follows with this task solution. So we observed a whole bunch of tasks in 3 lizards, about 70 trials, and found basically that if you describe the task space by body angle as a function of time and the velocity towards the cricket as a function of time, we see a pretty stereotyped or consistent task behavior. So not only is the variance around the mean pretty small, but there's a consistent strategy, which is sort of this parallel turning and acceleration. You never really see them turn around in place and then accelerate, or any of the other possible strategies you can imagine. So I would call this a pretty stereotyped task response. Is it robust? To find out, I put a slippery plate in various places around different feet and induced large slips of the feet, thereby sort of removing contact forces they might be using for maneuvering. But if you sort of, you probably saw that video, it looks qualitatively similar. In fact, here are 2 example trials, sort of typical trials, unperturbed on the left and perturbed on the right, and they seem to be about the same in their task execution. In fact, if we plot in their sort of task space those 2 exemplars, they're almost identical to the average task trajectory. And if you plot across all the unperturbed and 40 new perturbed trials, the means are essentially identical across the execution of the task. So really no significant difference in the way perturbed animals are solving the same task. So this was really surprising to me, obviously, and it kind of breaks my fundamental assumption, which is that this is a really high-effort task. It's basically the most aggressive task we can get them to do, and still, they're able to lose contact, lose forces for a whole step, and not lose task performance. So to take a little closer look, I measured single-leg ground reaction forces using a small force platform inserted underneath individual feet. And even more confusingly, I found that unperturbed contacts are also highly variable. So here's just one sort of slice of that data. This is the angular impulse that foot is doing about the center of mass for front, hind, and sort of limbs on the inside and outside of the turn. And we see there's definitely a strong average pattern, but we see also huge variation. Sorry, you probably can't really see my pointer here. huge variation around that steady pattern. This foot that can generate the largest forces also often generates no force, which is really strange. To see if they were compensating somehow in their gait pattern, we looked at sort of gait diagrams for these transition behaviors. Here again is the feet front and hind, inside and outside of the turn as a function of time. Black bars indicate contact. And what we see is sort of they all start in that steady motion. They go through a transition step, and then they transition to something that looks like basically steady running. This looks like a trot, so if they'd kept going, you'd see these alternating diagonal pairs of limb contacts. That was the unperturbed trial. Here's the perturbed trial. It looks about the same at the beginning and at the end, but what we do notice is that there are big differences in that transition step. So here you can see there's actually an extra contact period, and there's big phase shifts and things going around. So potentially, the gait is also not well stereotyped. But it's not random. There is something going on here. So to take a look at the sort of average picture, I built up kind of an average gait diagram over all these unperturbed trials. Again, here we have black means contact, but that would be black would mean that every trial had contact at that particular time, and white, every trial was lifted. So a perfect stereotyped gait would be perfect black and white gait diagram. But in practice, what we get is a sort of shades of gray or shades of red, as the case may be here. There is an average pattern, so you can see sort of trot pairs here. But around that pattern is high variation, just like we saw in the low effort kind of cases. So essentially still this really messy gait, even at the sort of highest efforts we can get. So lizards essentially solve this really high effort task the way they solve this low effort task, which is robustly and flexibly. But how do they do it? The answer is I don't know. And I have lots of thoughts and hypotheses I would like to talk to you about. I think I'll just throw these up and we can chat about them in the question time, so I'll thank you for your attention.
We have plenty of time for questions.
Any questions? Question might be, when is lunch? Is after 2 more talks?
You have 3 talks left.
If you go back to the video on the perturbation slide.
The perturbations? Yeah, okay.
Yeah. It looks like
you want this one?
It looks like it's avoiding the slipping. Oh.
Or do you want maybe?
It looks like it kind of is on like the.
Two various. Yeah, so the slippery patch, and not only does it perturb the feet, it perturbs them in the sense that they step around it. So they know it's there. They change what they do with their legs.
Are you studying like the lack of contact forces by it putting its foot on the platform, or its ability to avoid the slippery platform altogether? So
I think both, basically, right? Because essentially the same thing is happening to them in their unperturbed trials. So they always have little micro slips. I think this sort of one of the hypotheses, one of the many hypotheses that I say of why this might be happening here is because maybe they always slip a lot, right? Maybe they're always experiencing things that they need to change about their gait. And that's, so that essentially what we're seeing with these perturbations is they just sort of fall in the natural range of perturbations they experience. And that's why it's not degrading task. It's really more about robustness.
Can you pass it back to Jonathan? Ooh, blocked by the pole. We're getting there.
So if you change your perspective of how you're looking at this, because we're watching this video, and so inherently we're looking at the positions of all of the limbs. But if instead you look at the force being applied by each limb on the ground, is it really that different? Are they able to get enough of a frictional contact as they slide across a steel plate that the forces are just about the same as they were before?
Yeah, I think that's a good question, and it's something I couldn't really measure with the setup I had here. I think that the one piece of evidence I have that this is a pretty strong perturbation is that if you make that plate really big, and I should have had this as a backup slide, if you put the lizard on a flat oiled steel plate, they just scramble around and they can't do anything. So I think that they really are losing contact forces. I think that those lost contact forces are sort of in the spectrum of what we're seeing here, which is that the animals often lose contact forces even when they have traction.
All right. Greg, why don't you do one? And John, if you can pass back behind you. There's someone behind you that had a question.
You stole it. I was going to say that.
Okay. Well, no, let's do Greg first.
We're doing Greg first. Whoa. Nice catch.
Would they exploit a stickier contact?
Sorry, say again?
Do you think they'd exploit a stickier contact?
Yeah, that's a good question. We experimented a long time with traction surfaces that would try to maximize their contact. And basically anything rough enough or corky, something they can get their claws into, seemed to be about the same. So this sort of substrate that we had them on there was a sandy, rough substrate mixed into paint, which seemed to be good enough to get claws into. But I could never really get them to do better than that. So like giving them something really grippy, like soft plastic or rubber, just didn't really seem to increase the performance or the stereotyping.
Oh, Chris, all the way back. Do you want to project, Chris?
Yes. I think you're insulting the lizard's intelligence. These lizards are perfectly capable of scrambling along very small tree branches and doing amazing things. And here you're asking them to just operate on level floors. And of course they put no effort into it. Of course they don't try hard. Why should they? So, if you don't ask a lizard to do something tough, they're not going to give you high performance control.
Yeah, so yeah, I think that's an interesting question. I mean, it's true. They may just be leaving something in the tank, right? That's definitely a possibility, and that's why they're able to maintain this robustness. But I disagree that this is not a hard task. So I showed you the ones that they actually got. At least 2/3 of the time that we threw the cricket, they just missed it completely because crickets are also fast. They get away if you don't catch them in 100, 200 milliseconds before they land. So I still think this is a pretty tough task, especially with the slippery perturbation in there.
Russ.
So I feel like a big difference between the periodic task in walking and the sort of one-shot task you're doing here is that you can't control your initial conditions very well. So do you have a sense from your data how much of the variability is just coming from the initial conditions? And you could you even, if it's, how well can you control their initial conditions? Maybe you're controlling the heading initial condition very well, but the leg position not very well.
Yeah, this is a good question. So they're always starting at rest at least, so we only have to think about posture. And we tried our hardest to get them to start in, I sort of, glossed over a lot of the sausage making, right? But like they're standing on a forced platform or a slippery platform, and so we're kind of coercing them into a particular position and then getting them to do this behavior. And so we tried to sort of get their bodies sort of lined up straight with no big tail flexion, and we tried to get all the limbs in one place. But inevitably, they do have this sort of postural variation. Because they don't sit like a robot at a very particular prescribed posture at the beginning. So I think a lot of what we're seeing in terms of those contact forces that are just zero in some cases is that their leg was just in a posture they didn't like, and so they just lifted it up and replaced it, right? Or they just, they start to move it a little bit and they get some sensory feedback that it's not working out, and then they move it somewhere else. So
if you were to downsample your data across some postures that are pretty consistent, would you see less variability, right?
Yeah, I don't quite know how to do that. I would like to talk about that. That's an interesting question because there's, it's always a curse of dimensionality. There's a big posture space and not very many trials, so.
Let's do the guy in the light blue shirt. Oops, sorry, didn't get enough on that. And then Noah after that.
Hey, Jeff.
Hey, Tom. Yeah, it seems like in this experiment, the lizards are the predators. So they're very motivated, but it's not life critical for them to get to the goal. If they were the prey and you initiated some prey response, would you expect to see anything in the tank? And I would certainly think the slipping would matter.
Good question. And if you look at most of the biomechanics literature, people tend to use escape responses to induce behaviors in animals. So I actually started with escape responses to try to probe this question. And the answer was it was incredibly variable because then they just want to get away from you. And there are lots of ways that they can get away from you. So they can just jump straight backwards or run sideways, or they can, they jump straight up in the air. Like they have a much bigger solution space for getting away from you than they do for getting to a target. So it's actually, I think, much worse.
All right, we'll do one more from Noah while the next speaker gets set up.
All right.
So did you look, you said anecdotally you saw a lot of evidence that they were using feedback control. Did you try to look at any metrics such as, mean time to foot liftoff for when it's on the slippery thing versus not, to get a measure of like some sort of bound on the latency and whether or not they're using feedback?
Yeah, so I think you're right. I think they're definitely using feedback, at least stride-to-stride level feedback. The gait frequency, like the average sort of time for a full cycle, is about 6 hertz on some cases, 4 to 6 hertz. So, just in terms of making ballpark latency numbers, I'd say that they almost certainly can't do within stride feedback. But like if a foot starts to slip, there's probably not much that they'll really be able to do to change that before the step is over. But step-to-step feedback is definitely in the realm of possibility.
Great. Thank you, Tom.
Thank you.